Hola, my name is Pamela. Welcome to my channel. Today I'm gonna talk about this standard applied to the calculation of the differential pressure elements for compressible fluids that pass through a nozzle, orifice, or venturi tube indicates that these are the formulas to calculate the volumetric and mass flow respectively. Now, to calculate the dimensions of the element, we clear the term beta squared from the previous formulas, resulting in the formulas that you can see, in which the second term is already known. Now, the final diameter ratio of the selected primary element is determined by successive approximations according to the approximation desired in the calculation, which is usually 0.01%. If we want to make a quick calculation of the differential pressure element, it is enough that we consider that the discharge coefficient of the orifice plate is 0, and that of the nozzle and venturi tube of 1, and that the approach speed is equal to 1, these being the formulas with which we do the calculation. Now we will do the normal calculation of the element, and for this, step 1, we calculate the diameter of the pipe with this formula, that considers the temperature of the fluid. Step 2, we calculate the Reynolds number. Step 3, we calculate an approximate value of beta, for which this graph is consulted. In this, the upper and lower limits of the Reynolds number are indicated to check the limits of its values with the relation to beta. Now, this table provides the maximum values of the relative roughness K over D of the pipe can have for a distance of 10 pipe diameters upstream from the orifice plate to comply with the ISO standard. In step 4, the expansion factor E is calculated from the beta value that we already calculated, while the isentropic coefficient X, which is the ratio of specific heads at constant pressure and volume, is calculated in this table. In step 5, we calculate the discharge coefficient C. If the diameter D at the fluid flow temperature is less than or equal to 58.615 mm, the coefficient 2.286 will change to 0.39. Step 6. A new beta value is calculated with this formula, where Fs is a correction factor used when the fluid is water vapor with a moisture content W1. For liquid and gas, Fs is equal to 1. Then, the calculations of points 4 to 6 are repeated with this new beta until the obtained value of beta approaches 100. In step 7, the diameter of the hole is calculated at the service temperature of the fluid. In step 8, the diameter of the hole to be machined is calculated, where h is the coefficient of expansion of the plate. The calculation for the 1932 ISA nozzle and the venturi tube are similar, with the difference of the values in step 4 and of C in step 5. To calculate the global error of the measure of a differential pressure object, we use this formula. The error in the discharge coefficient C is plus minus 0.6% in the orifice plate, plus minus 0.8% in the ISO 1932 nozzle, and between plus minus 0.7% and plus minus 1.5% in the venturi tube. The error in the expansion factor for each of these elements is this, and all of them within the beta limitations ranging from 0.3 to 0.8%. The error in the diameters in the pipe and in the orifice is the root mean square value of the micromagnetic measurements made. The error in the differential pressure P1 minus P2 is given by the precision of the device, which is typically plus minus 0.1% and plus minus 0.5%. The error in the density measurement is given by the density instrument or the pressure and temperature compensation devices, in which case the root mean square of the corresponding pressures is added. As we can see in the simplified general flow formula, the measurements depend on the density of the fluid, so if it changes, the reading of the instrument varies. To make the calculation, we start from the previous data that are taken and that are the closest to the real ones. If the actual density deviates from that taken for the calculation, a correction factor must be added. We have that the real flow is calculated with this formula and the flow rate with this other, being Pc the density that was taken to calculate the diaphragm. Then the calculation of the real flow based on the flow rate with the correction factor would be like this, being this the correction factor. In the case of liquids, it is easy to make the correction because it is easier to measure the real density. In the case of saturated steam, it is enough to know its temperature or pressure using tables. The same if it is overheated. When the fluid to be measured is a gas, its density is determined according to its composition, carried out with chemical analysis according to this formula. If the gas is ideal, its density at the temperature and pressure as it is passes to the diaphragm is calculated with this order, while the density of the gas is calculated with this one. Since the value deduced from the flow QR in cubic meters per hour, based on the flow rate is this. The correction factor will be like this if the humidity of the gas taken in the calculation is Hc in newtons cubic meters per hour of dry gas, and if the real humidity turns out to be Hr. If the fluid temperature varies a lot in relation to the one considered in the calculation, the calculated diameter will deviate from the real one under the service conditions, leaving the flow correction factor like this. If the gas carries particles of suspension that settles on the walls of the pipe, particularly in the lower part, the internal diameter of the pipe gradually reduces, which affects the reading. If cleaning is difficult, it's best to determine a correction factor, for which we use the following formula to calculate the diameter of the pipe at the time t. Then we can conclude that the general formula would look like this, and that its corresponding correction factor would be the one below. And well, this will be all for today's video. Don't forget to give me a like and subscribe. I upload videos every Wednesday in Spanish and every Friday in English. Adiós! Which is usually 0.0. And of C in the state C, and between plus minus 0 and that are